Hi everybody, my name's Dermot O'Shea and I'm the host of the Antenna podcast, and today I'm delighted to be with Michael McLaughlin. Michael, would you like to introduce yourself and tell us a little bit more about you?
Yeah, so I was the CTO of Decawave, and Decawave is an ultra-wideband company, and we basically brought ultra-wideband to the world, and now it's on every smartphone and every high-end car auto-opening device. What do you call it?
Key fobs. Yeah.
Key fobs, yeah.
Yeah.
So I started by going to standards organizations, the IEEE 802.15.4a, and I got my ideas into the standard and I had them patented, and then Kieran Connell joined me and we started Decawave, and we started hiring people. That was in 2004. I started going to the standards meetings. 2007, the standards published and Kieran joined me, and then we started to build up the company. 2009, we had our first prototype on FPGA. We used an antenna that we still actually use to this day. Ultra-wideband, as the name implies, it is very wide bandwidth, and you don't want a tuned antenna that's tuned to any particular frequency. So it's kind of a gather everything, but not quite. That there is a band, and so that antenna was designed by Max Ammon in DIT
Here in Dublin.
Yeah.
Yeah. So we're just to maybe mention it to listeners, we're here at the EU CAP, which is the conference on antennas and propagation, which Michael had a keynote at. So, and which Max Ammon is a professor here in DIT, Dublin Institute of Technology, that we've both worked with. Yeah, I remember that antenna design. Yeah.
Yeah, we called it the man antenna because it looks like a man.
Okay.
So the prototype had that antenna, and we kept actually using it, and we still use it. That was 2009, and then 2011 we had our first MPW, and 2013 we released our first production silicon. So there was 2 years.
And so, like, but in the phones, we have cellular, GPS, we have Wi-Fi, Bluetooth, NFC. Why do we need ultra wideband?
Yeah, everybody said you're mad. Nobody's going to put another radio on the phone, like just everybody, and that's why VCs wouldn't give us any funding. So, 2011, we persuaded Apple to come over, and we said, you really need to see this ultra wideband because you really need to put it on your phone. And Kieran likes to say they gave the company a colonoscopy. they looked at us upside down, inside out. They just gave the company a complete once over, and we were kind of with them. That they brought their engineers over, and they interviewed us all, and we were hoping they'd buy us for a lot of money, and. But they didn't. They just went away, and so we thought no more about that. But something landed with them, because in 2019 they brought out an iPhone, September 2019, and it had ultra wideband on it. So it took them 4 years. They developed themselves. Did it their own way, but it followed the 4A standard, so we could actually talk to them then. And 5 months after that, Corvo bought Decawave for $400 million.
Great success for you guys. Congratulations.
Yeah. And we finally persuaded the VCs to come in 2016. When we were kind of close, we'd sold millions of chips. But at $1 a chip, millions of chips isn't enough. You need to sell billions of chips. So Apple, by putting it on the phone, they didn't just adopt ultra-wideband. They validated us. And as soon as they have it on their phone, everyone says, oh, what's this ultra-wideband? Samsung needs it on their phone. Google needs it on their phone. So so Corvo took us over and built up big software, because there's a lot of software that goes with that. Big software stacks in their in Paris and Toulouse, and we do all the semiconductor stuff in Dublin. There's about 100 of us in Dublin, and another 200 in Paris and Toulouse, and so it's been very good.
And for people not familiar with it, like on the iPhone, on your phone, I understand it's used for like applications like AirDrop when you want to. Is that correct?
Yeah, and Find My Stuff. So
Find My, okay.
So the Apple do these AirTags.
Oh yeah, yeah.
And I didn't bring my keys with me, but because I got a taxi in. But they're you put them on your keys, and then you can find your key, and it could be buried in a bag in the corner, and it'll tell you how far away it is and what direction it is.
Yeah.
And Google do something similar on their phones, and Samsung.
And so what kind of applications have you guys in Decawave now, Corvo, been involved in? If that's so,
automotive is our biggest one.
The key fobs, like you mentioned, yeah.
Yeah, and
what technology were they using before ultra wideband?
The cars.
Yeah,
they were using Bluetooth.
Okay.
But the problem was people were stealing cars. So what they do, somebody want to steal your car, and you'd put your keys on your nightstand, and it's up in your bedroom. So they just put an antenna up, and they'd put an antenna beside your car, and the car would be saying, is there anybody there? And they'd boost that signal, and the antenna would be saying, is there anybody there, to your nightstand. And it, of course, would reply, yeah, I'm here. And then they'd relay that. So cars were getting stolen left, right, and centre, all across the world. And it was all the luxury cars. But they kept it very quiet, the car industry, because they didn't want people to know this.
Yeah.
But what ultra-wideband does is it measures distance really accurately. So if I have an ultra-wideband chip, there's one on my iPhone. I don't know what phone you have.
iPhone, yeah.
There's one on your iPhone. So I can find your iPhone if you allow me to, and it'll tell me exactly where it is.
Like when you go to share the picture or share the file, it'll look for you'll see it come up as an option.
Yeah, but not just that. You can do Find My, and you can borrow your daughter's phone and find your own, and it'll. What it does is it sends this ultra-wideband signal, which are these really narrow pulses. So most communications, they spread the energy out over time, but with ultra-wideband, you concentrate it to these narrow pulses.
Okay.
Really wideband pulses, and the antenna needs to not delay the signal and not mess with the time. Doesn't matter about the frequency, but not mess with the time of arrival of these pulses.
So you need accurate. So how do you make sure that the time of arrival is accurate then, and how does the antenna play into that?
Fidelity.
Okay.
That I think Max Ammon actually came up with that term, the fidelity of the antenna. So it sends a signal over to that iPhone. That iPhone sends one back, and you multiply the time it takes by the speed of light, and that tells you what the distance is from here to there and back.
Okay.
So you can very accurately tell where it is, and then if you have two antennas, you you can use the phase of arrival of the signal to tell you the direction.
Okay.
So then you know exactly where it is.
So it's you can determine the position of the other device by using this fidelity and phase of the antenna.
Yeah.
Brilliant. Yeah, I haven't heard that term fidelity before.
Yeah. I'm not an antenna expert, so I don't know exactly how it's defined, but that's what Max Ammon came up with.
That's brilliant. Okay, so the antenna is important for you guys, even though...
Oh, it's really important, yeah. I was going to say something there. What was it?
When we were talking about fidelity and Max coming up.
Yeah. You said why did the cars? So the cars are getting stolen left, right, and centre, and the way around that was ultra wideband. So now you that relay between the key fob and the car, you measure the time it takes. So you know that the person's right beside the car, and you'll only open the car if he's within a certain distance.
Yeah, because when they did the antenna relay, it takes more time.
Yeah.
You know how long that takes.
Exactly.
So it times out basically.
Yeah, so it says that's too far away, I'm not opening the door.
Brilliant. Yeah, I hadn't heard much about the car, because we've obviously doing antennas, since we started to come to Hourglass, we were involved in stolen vehicle tracking systems.
Yeah.
All that type of stuff, but I hadn't heard about that issue with the key fob. So you're right, they did really keep it quiet.
Yeah, and so Jaguar Land Rover came to us, and they'd seen and they said, hey, we could use this to solve our problem. And they brought a Jaguar over to Dublin, and we did all these tests. They put our prototypes in, and with that man antenna, and measured all kinds of things, and got channel impulse responses between the car, inside the car and outside the car, and all kinds of stuff. And they were our first big customer for the chip, and they came out with it first. And so if you look at, there's a 2017 report on stolen luxury cars, and the Jaguar Land Rover models that had this in it, it's practically zero.
Oh, brilliant.
And all the others are really high. And it's because they did that.
That's like, it reminds me of another customer we have called Gatekeeper Systems, who do basically a shopping cart system that locks when you try and walk out of the shopping centre with the shopping cart. And the way they've drove their business is when you install their system, your theft goes way down, and the other store's theft goes way up, because the criminals know you have that system, and so it's driving their sales. Yeah.
That's exactly the same thing.
Yeah.
So they don't go near Jaguars anymore. Do you remember I had a Honda Civic years ago, and Honda Civics were the car to steal by the joyriders.
Right.
And of course ours was. Everybody said, "Don't buy a Honda Civic." It was stolen from the car park in a big shopping centre. We came out of the shopping centre with the shopping. Where's the car? It's gone.
Gone. Lord. Okay. Yeah. Used to be a big problem. So I'm glad to hear you guys helped us resolve it. And then how did you get in? How did you come up with this idea, and how did you get into this business? Where were you before Decawave?
Yeah. So I spent 18 years in Cornell Electronics, which was bought by Lake Datacoms.
Okay.
And that business kind of fizzled out, and I moved to Parthas. And it was actually when I was at Parthas that I got interested in ultra wideband. Dave Maloney, I don't know if you know Dave Maloney.
Yeah, I remember the name. Yeah.
He said, Michael, this ultra wideband stuff looks really good. Will you have a look at that? And it ended up that Parthas didn't do anything with it, but they made everybody in Dublin redundant, and I used my redundancy package to fund me while I went to these standards meetings.
Very good.
For ultra wideband.
Never waste a good crisis, as they say.
Yeah.
Yeah. Very good. And you went to UCD like myself. I see the badge.
Yeah.
Here, yeah. And why are you here at the Antennas and Propagation Conference?
I gave a keynote speech about a new code I just came up with recently, a couple of years ago, CZC codes, and it's a way of doing channel sounding, and with no interference. So I have a paper in the conference about these codes, but it's a keynote paper, and as the keynote speaker, I opened the conference here. I just told the Decawave story and how the keynote's called "Think Like a Builder," and that's my philosophy in engineering. Don't think like theory. You need a really good understanding of theory, but until you start building something, you're never going to find the real problems and solve the real problems that happen in real life. So you have to think like a builder. The architect can draw these beautiful plans, but the builder is on site and he has to fit these pipes around corners, and spaces are tighter than predicted, and he can see everything. So you have to think, how would a builder solve this? Don't say to yourself, I wonder, has anybody else solved this problem, and go and look up a book. Think yourself, how do I solve this? And after you've thought about it for a while, then go and look at the book. Because if you look at the book first, you'll get driven down in a certain direction. And if you let yourself think like the builder does about how you would solve the problem first, and then go to the theory.
Yeah, that's a great analogy, because we always like to say, like, we look for engineers that are creative, you know, in how they approach problem solving, rather than, you know what I mean? Like, yes, you have to have the theory as a background, but you have to have creativity, because each problem and challenge is different, and then experience. Like, there's nothing like experience of like hundreds of different projects where you've met all these problems, and you've gotten around them in different ways.
Very true, yeah.
And like, that's what I say. Like, the guys here, we have a AI integration engine and stuff on our website, and they're joking that AI will replace us, and I'm like going, they're definitely not replacing engineering. We need more and more of it. So yeah, it's a great analogy.
It's a big help, but you can't believe what it's saying. You can't just take it. You can get it to help you reword a sentence, or write a really tight, efficient piece of code. But you have to tell it what you want the code to do. I use AI to write huge amounts of code now, but you can't let it have its own free reign, and it's never going to replace me.
Yeah, that's it. And you made it sound easy there, like when you described the Decawave journey briefly, but I'd imagine it was a lot tougher than that. But what project?
Yeah, that 12 years, it was so tough because we had no funding from VCs until 2016. So that was 7 years after we started.
Right. And how did you survive, like, from cash perspective?
It was all angel investors.
Okay.
We had over 200 angels, and nobody's ever seen anything like it.
So it's like fundraising every day.
Yeah, Kieran is a master at that. And
okay. So you were able to focus on the technology. He was doing, okay. So it was a good partnership that way.
Yeah.
Very good.
And he's a big what's a big thinker about like where is Decawave going to fit in this world? He thinks about all that kind of stuff, whereas I just solve the technical problems. And
okay, so you had the key fobs, a big success for you guys.
Another thing I just wanted to say, in 2011 we'd completely run out of money, and we were hoping there was money coming soon. Nobody got paid for 4 months Some of us 5 months.
Wow.
Not a paycheck, and that's a long time.
That's a long time, yeah.
Especially if you've got young kids, and but not one person left.
Wow. That's how many people was that with no paycheck?
14.
That's insane. Yeah,
Yeah.
because when we started Toudlas, we had no paycheck for 2 years, but it was just me.
Wow.
Me and my co-founder Ronan, that was it. There was only two of us that time, so that's a bit easier to manage. And that was before we had kids. But yeah, I can't imagine 14 people. That's some dedication.
Yeah, they all believed in myself and Kieran.
And the technology too.
And the technology, yeah.
That's brilliant. That's an inspirational story. So
Yeah.
I think that's what we're getting from the Antenna podcast here today. It's more of a entrepreneurial podcast and a story of resilience, yeah. And so do you have the key fobs as a big success? What are you working on next? Like, what do you see is good future prospects for ultra wideband?
Yeah, well, the car is our biggest market at the moment.
Okay.
And we're focusing on that. But ultra wideband, nearly everybody you talk to, if it can measure the distance and the angle, nearly everybody can come up with, oh, that'd be really useful for X or Y.
Gotcha.
Like finding stuff, opening cars, making sure your dog doesn't get too far away from you.
Indoor positioning applications, like we've seen it in sports, right? Indoor sports where the GPS can't solve the athlete being tracked in an indoor arena.
Yeah, if you look at all the soccer teams and rugby teams, they all have this little pouch in the back here. Each of those pouches has an ultra wideband chip inside it, and then there's antennas all around the stadium. So they're analysing where each player has gone in 3 dimensions to really high accuracy. You know that they do thousands of scans a minute or a second for every player. So they know speed in 3 dimensions, and there's one in the football. The World Cup, the last World Cup, had microchips inside the football.
So
with
the speed,
antennas.
it's measuring the speed of when the free kicks were being taken. It's giving you the speed and the...
telling you whether it was a goal or not. Did it go over the line?
Oh, yeah. That was actually, that was great technology, yeah.
Yeah.
That was
that was us.
Brilliant.
Our chip was inside the football. And antennas from DIT.
That's brilliant. Great story. And so on the for
people want to put it in golf balls as well.
And could you do it in a golf ball?
No, because the compression is
speed and the distance.
Have you ever seen a golf ball in slow motion? It goes to nearly flat when it's against the face of the club. So I don't think anybody has overcome the mechanical problems.
Is it? What about tennis? Be useful in tennis?
Yeah, that could work.
Yeah. Okay. And that's so. I see you guys talk about in your technical description of the product the angle of arrival a lot.
Yeah.
So that's basically you're measuring the angle of where the antenna is transmitting from. Is it? Or give us the maybe.
It's actually phase difference of arrival.
Okay.
So and from that you can work out the angle.
Okay.
So if you imagine there's a sine wave coming in from the transmitting antenna, and it's hitting both receiving antennas, and if they're both like this, then the phase is going to be the same. But if you move one slightly forward, then it's going to hit this first, and the phase will be slightly advanced on this one. It'll hit this second, so the phase is later.
So you're not changing the polarization of the antennas, you're just changing the distance away from the transmitting antenna.
Yeah, because if it rotates, it naturally moves a little bit further away.
Okay.
And that gives you a phase difference between the incident wave at the 2 antennas.
Okay. And then the angle of arrival is what?
And then you can work out from that phase difference what angle the antenna's at. Because if it's face on, there'll be 0 phase difference. If it's like this, so let's say that the antennas are half a wavelength apart. It'll be 180 degrees.
Okay.
It'll be half a wavelength.
Okay. And then what kind of antennas are on the base? Would you call them base stations or beacons? What do you call the?
Yeah, we call those the anchors.
The anchors. Okay.
And
how many of those would you need in a stadium, roughly?
It depends. With this in the 4A standard, you needed a lot more. There's a new standard that's come along, 4AB, and it's just been published. It's either this month or next. It's around now. It's going to be published. But the work was all done years ago because there's all this rubber stamping on it.
Yeah, it takes time. Yeah.
So with it, you can see a signal that's minus 123 dBm. Because it's the techniques that it uses, and the thermal noise for our bandwidth is minus 87 dBm. So you're that's 36 dBs below the noise. So it's a really, really weak signal.
Okay.
And you need much less antennas when you can do that.
Okay.
But with it all depends how big the room is, obviously. The minimum is 3, so you can get 3 dimensions.
And these are directional kind of panel type antennas what they look like? What do the antennas look like on the anchors?
It depends. There's 2 ways of doing it. One way is you can measure the. If you take you can do it without angle of arrival, just by measuring the distance to each one.
Okay.
And if you have 3, then
you triangulate.
Yeah. But usually you need more than that so that you have redundant information and you can throw away bad measurements.
Okay. Yeah, because you might have reflections and multipath and all sorts.
Yeah.
Okay.
And if something's hidden behind a piece of metal, which is going to happen in any modern environment, then you'll only see the reflection. You won't see no matter how good you are, there's no signal there and you won't see it. And
do you provide the anchors as well, or is the chip that goes in the device itself?
Our customers that provide the anchors.
Okay.
And our customers provide the tags that the anchors are looking for.
Okay.
Usually it's tags, like cows is a big one. Can you imagine a dairy farm where there's hundreds or thousands of cows?
I do, because I grew up in rural Ireland. So
okay, yeah.
My dad was a vet, so he would do TB testing of cattle, and I'd have to note down the herd numbers. So it would have been very useful if we had technology to do that rather than wrestling with cows and trying to read their tags.
So you want to know, and so you know where all the cows are.
Yeah.
So if you want Daisy, say, Daisy's over in that corner over there. But as well as that, you can monitor their feeding and how often they go to feed, and a lot of people don't know this, but you probably do. Cows, when they're ready to milk, they go to the milking machine themselves.
Yeah.
And the machine comes, takes all the milk away, and they wander off. If there's a cow that's slow to go to its feed or slow to get milked, then there's something wrong. And you can preempt some kind of disease or just normal sickness, and fix the cow up, call your father.
Yeah, he was getting called anyway, yeah. So, okay, I think we could talk about this all day, but I think we'll wrap it up there. Michael, thanks very much. Just a quick question on advice on, it's a really interesting technology, and I'm sure people would be curious. What advice could you give anybody that would like to get into this industry or find out more? Like, what's the kind of, what would you study in college, and how do you get your way into these types of technologies?
Yeah, well, you probably had the same teacher, but Tony Fagan was my lecturer in antennas and propagation.
Okay.
And I used to love that subject, and he later joined. Gave us advice. Decawave. He's very supportive of Irish industry, and so understand antennas and propagation. It's a fascinating subject, and it's when you're thinking about it, you can think about relativity and light and photons, and I find it really interesting from that point of view. But mathematics, you need a lot of mathematics.
Yeah.
And then, but the biggest thing is optimism.
Okay.
And take a risk. If it doesn't work, it didn't work. Take another risk.
Okay.
I'm sure you're.
So don't, failure is just the way it's it's directing you on the right way to go.
Yeah. Wasn't it Edison who said, "I didn't fail to show how light bulbs work. I didn't have 1,000 failures. I now know 1,000 ways it doesn't work."
Okay.
I think that's really good advice.
Yeah, it's like Michael Jordan, and how many, they looked at the stats of how many shots he missed, you know what I mean, in basketball games, and I think it was like 40% of the shots he took he missed. But nobody ever remembers him for that.
Same as with tennis players.
Yeah.
Roger Federer, he only wins 55% of points.
Yeah, there you go. Yeah, 'cause a lot of people would be thinking about all the ones you missed rather than all the ones you got.
Yeah.
Great advice. And how do people?
If people taking penalties, there's two types of people to take penalties in a penalty shootout. There's the guy who thinks this is an opportunity to score, and that's the
optimist. Yeah.
That's the what do you call him? What do you call that guy from Portugal?
Oh yeah, Ronaldo.
That's his. Here's an opportunity to score a goal. Whereas the pessimist is thinking, here's an opportunity to make a right arse of myself and put it over the bar.
Yeah. So and you can see it sometimes when they're stepping up. If that's in your head, you're gone. Yeah.
Yeah.
I've been thinking about that now. The next time we're assigning antenna projects, and where can we find out more then about your technology, which is now Qorvo? I presume it's on the website.
Qorvo.com. Yeah.
Qorvo.com.
QORVO.
QORVO. Listen, this is Michael McLaughlin. Thanks very much. It's been great. I'm Dermot O'Shea, the host of the Antenna Podcast, and thanks very much for taking the time to talk to us.
Thanks, Dermot. Lovely to talk to you.